Without further ado, I'd like to first introduce our first Gilbreth lecturer, Dr. Jesse Quinlan. All right. Jesse is the program technologist for NASA's Advanced Air Vehicles Program Office, where he leads technical strategy and advises leadership on technology development efforts spanning subsonic to hypersonic air vehicle applications. He earned his doctorate in mechanical and aerospace engineering from the University of Virginia. Jesse will give us an overview of new air vehicle concepts and technologies that will revolutionize aerial mobility. Please join me in welcoming Jesse to the stage.
Thank you so much for the introduction. It's such an honor to be here, surrounded by so many esteemed members of the NAE, and I love the energy of this meeting today, looking at all the high schoolers in the crowd here. And I have to acknowledge that I'm standing between everybody here and a break, so I'm going to try really hard to stay on time. I want to start by setting the stage with a question. I'd like you all to think about how many gallons of jet fuel is consumed globally every year by commercial aviation. It's a lot, right? It's almost 100 billion gallons per year, okay? All right, so for extra credit, another question. How many Olympic-sized swimming pools is that? 150,000, okay? So when I think about revolutionizing future aerial mobility and commercial aviation through technology innovation, I look at that immense challenge and immense opportunity to improve the way we fly our aircraft, to improve the efficiency of our vehicles, and ultimately help us achieve aviation sustainability in the far term. And so there's a huge opportunity there. I bet a lot of you probably recognize this picture here. And I wanted to show this picture for two reasons. One, as I reflect on my career and what I've learned in the past 20 years, when I think about technology development, I think about how nonlinear it is and how overnight the near impossible can become possible. And so in 1903, the first powered flight happened, and before that, it was impossible, and afterwards, well, look where we are today. I think many in the room here probably flew here from across the country, just like I did, and we take for granted now how safe and reliable and efficient our air transport system is. But we've come a long way in just 120 years. The second point I wanted to make is we have a huge challenge ahead of us, and I'm going to talk a lot about that here. I want to point to something a little bit more personal, especially to the students in the room. We need bright engineers. We need to prepare the next generation. And one thing that I think we all need to think about is mentorship. I take this very, very personally. I'm a first-generation college student. I come from a very small rural town in Virginia. If it weren't for early teachers that took interest and understood I wasn't being challenged and brought me to the side and mentored me, if it wasn't for college professors that did the same, I still have mentors today, and you're never too old to have a mentor. So I just encourage you all to think about who that is in your life that you can trust to help you understand what you're capable of. Whether you're a high school student, mid-career, senior leader, it doesn't really matter. So first, I'm going to talk about the aviation challenge that I think could be the aviation challenge of the century, and that is sustainability. I already mentioned that nearly 100 billion gallons of jet fuel is consumed every year. That is expected to grow. Air travel demand is expected to grow. If you look at the chart on the screen here, this is CO2 emissions on the y-axis and time on the x-axis. If you look at those curves out to the right, we're probably going to experience significant growth year over year as the demand for air travel increases. And already we contribute up to 3% of CO2 to essentially the globe right now, which may sound like a small number, but let me put an idea in your head. As other sectors that are easier to decarbonize do decarbonize, that 3% fraction that we contribute in aviation is going to continue to grow. Another point about aviation and emissions and the grand challenge here is it's just an incredibly complex problem. We take for granted in some ways how safe and reliable and efficient our airplanes are today. And it takes a lot to overcome some of that inertia in the system and disrupt, improve, innovate. But there are options out there in the future, and I'll talk to some of those. We also have to acknowledge that it's not just emissions when we talk about sustainability. In fact, the future is getting more and more complex. We think of it in terms of environmental sustainability as much as we do societal sustainability and economic sustainability, meaning that we want to preserve the ability to be mobile by air. We don't want to limit air travel, but at the same time, we understand the impact that it has on the world. And the climate is changing. It's increasingly changing. This is an existential problem that we have to solve. It also has to benefit the bottom line because companies make money. They don't make money, they go out of business. And so there's this interesting interplay between these three forces of sustainability that we have to consider. And even more so now in our current environment, finding ways to tell a message around energy security and resilience and operability. In addition to economic competitiveness and global compatibility, understanding the supply chain side of commercial aviation and the limitations around rare earth metals and some of the geopolitical concerns around things like that. The future's growing more and more complex, and the problems aren't getting easier. When we think about how we would go about solving the aviation sustainability problem, I think it's helpful to look at where the fuel is being burnt. So fuel is correlated to emissions and is correlated to costs, and so if we can identify, let's say, the biggest offenders, maybe that's where we start investing. And if you look at the pie chart on the screen here, this is a pie chart that represents the relative fuel burn per class of aircraft. And if you look, there's 2 or 3 really big wedges there. And the summary is that most of the fuel burnt in aviation is really burnt on airplanes that carry more than 125 passengers. So these are the 737s or A320s that you might have flown here on, or the 787s or larger. And so if we're going to invest in technology development to solve the aviation sustainability problem, we need to start and hit where it hurts, right here on the single aisle and larger vehicles. Another interesting thing to look at is historical fuel burn. And when we go back 60 or 70 years, we can make a case for really, just substantial year-over-year improvement. We've had about 1% reduction to fuel burn in the fleet nearly every year on average. But I'd posit that at some point, if you don't change your configuration, you'll start reaching diminishing returns. And so if you look at any airport today, you'll see airplanes that look like a tube and a wing, meaning a cantilevered wing with a pressurized circular fuselage sitting on top of it, with turbofans or perhaps turboprops under the wing. At some point, you start reaching natural limits of a configuration or a design, and we're, I think, getting close to that point. And so I'm going to make the case, and we're making the case at NASA Aeronautics, that we need to be exploring transformative far-term vehicle technologies that perhaps disrupt what we consider to be the configurations we fly today. We also like to think of the opportunity here in the form of eras, 3 eras. And so if you look around today, we're maybe in era 1, which I would characterize as evolution. So tube and wing, perhaps some adoption of synthetic aviation fuels or sustainable aviation fuels, maybe some mild hybridization from an electric aircraft integration point of view, but largely we're going to keep flying the airplanes that we have today until they're out of service. Era 2, though, when we look to the 2030s, I think there's an opportunity to start revolutionizing aircraft and how we fly them, and perhaps looking to mild vehicle architecture change and maybe more significant SAF adoption, but there's challenges there that we can get into later, and other things. And I'll contrast that to the 2040s and perhaps the mid-century, where we're beginning to really explore the possible, and where we think that there's an opportunity to truly transform commercial aviation, where we go beyond the tube and wing, perhaps beyond truss-braced wings, and to truly unconventional configurations, perhaps even multi-megawatt EAP, electrified aircraft propulsion systems, and perhaps even alternative fuels. So SAFs are a lot like jet fuels. They're very different from cryogenic hydrogen and cryogenic methane. So if you keep these three areas in mind, that's going to help as we go through the rest of the talk here. I'm going to talk about the work we're doing to revolutionize in the 2030s, and then we'll talk a little bit about the work that we're doing to transform in the 2040s commercial aviation. One other point on this chart before I leave it, aircraft fly for a really long time in service. And so if you really want to make an impact, you have to start early. And if you think about the technology development cycle involved, this is a 15 to 20 year cycle that has to begin and be sustained and nurtured. And we're just really kicking off this transformative technology design cycle now. And I'll show a couple studies at the end that we're doing. Another thing that we do at NASA, being a government agency and often sitting at the intersection of industry and academia and other government agencies, is we take the lead in establishing goals to drive technology development for industry. You can imagine that many of our partners are very interested in certifying their next aircraft or re-engineering their current aircraft or focusing on the very near-term needs and realities of a business. But if you're not pushing, then we may get complacent. We may not disrupt in the way that we need to disrupt. And so we put forth goals that we communicate to our stakeholders. And this is an example of these goals, where we identify in the midterm and the far term really aggressive technology, vehicle technology level goals, but that are achievable. And we think these are achievable, but only with innovative technology development. If we take a look at just one of these lines on the chart, the energy consumption line, the way we go about establishing these goals is by taking a look at all the work that we can get our hands on. And on this chart, I know it's a little bit busy. This is the CO2 Cape 10 standard metric. What I want you to take away is, in order to get below those colored lines, you have to start moving beyond tube and wing aircraft. You have to start disrupting what we would consider to be legacy architectures and really look for technologies that offer much more substantial benefit opportunities, and that will also require a lot more investment, a lot more money, and a lot more partnership. On the bottom of the chart there on the right, you'll see a transonic thrust-based wing on the left and a blended wing body on the right. These are two vehicle concepts that we are especially interested in and have work ongoing right now, which I'll talk about in a few moments. I'm going to talk about the work we're doing first that's focused on the 2030s and the opportunity to revolutionize aviation through tech innovation. And the best way to think about this is in terms of a vision system. And so this is what I would call a vision system concept on the chart here. This is a transonic thrust-braced wing. You'll notice that the wing has an interesting looking structural member underneath of it. There's a couple other call-outs there I'm going to walk around and explain. We think there's maybe 4 or 5 really critical technologies that are worth developing now for potential entry into service in the 2030s. One is the transonic thrust-braced wing, which allows you to make your wing a lot longer, a lot thinner, a lot more slender. You can crank up your aerodynamic efficiency, and with the truss and the strut, you can keep the flexibility within check. Another interesting opportunity here is advanced propulsion systems. So moving toward more and more electrified aircraft propulsion and being able to achieve perhaps 5 to 10% fuel burn benefits over state of the art with that. Moving to open fan and open rotor propulsion system concepts. Moving to small core gas turbine engines so we can crank up the bypass ratio and get more efficiency out of our engine. And then at the end of the day, having to develop all these technologies with an eye toward being able to manufacture them as well. And so we have another internal project that's focused on high-rate advanced composite aircraft manufacturing that would ultimately enable a 4 to 6 times increase in manufacturing rate and help companies like Boeing, for example, meet the demand that they're unable to meet right now due to manufacturing processes. So all combined, if we succeed in developing these 4 or 5 technologies, we think we've got a shot at satisfying those midterm vehicle technology goals that we set in that prior table. We're doing all this work in close partnership with companies like Boeing and GE and others. And a lot of this work is leading to ground and potentially flight demonstrations in the late 2020s, which is really exciting. So that's sort of our midterm 2030s technology suite focus at the moment, and our teams are working this hard at the moment. Another interesting, important point here is that as we look at more and more unconventional aircraft configurations, the design challenges become different, and design tools that we used in the past become perhaps insufficient. And more we're moving to what I would call a digital engineering enterprise, where we have interoperable tools with multi-fidelity, multi-physics, multi-disciplines, and also design under uncertainty, understanding that we don't know everything. And in order to make an informed design decision or investment decision, we need to understand those uncertainty drivers. And so we have a team developing what we call the model-based systems analysis and engineering framework that is depicted here. So this is all with an eye toward the 2030s. Transforming beyond the 2030s is going to require even more radical exploration. And right now we have 5 studies with Boeing, Pratt & Whitney, Georgia Institute of Technology, Electra, where we're actually exploring the state of the art now and exploring what the state of the art could be in 2050. These are our ACES 2050 phase 1 studies. And those images on the top left of this chart depict some of those potential vision systems that these companies are exploring. So lifting bodies, blended wing bodies, cryogenic hydrogen and cryogenic methane propulsion systems, really advanced ideas and concepts that actually beg the question, well, even if you develop that for the vehicle itself, how do you enable it? How do you bring it to bear in a world that's based on jet fuel? So pretty quickly, the challenge becomes beyond the vehicle. It becomes a question of the airport, the infrastructure, the production side of it. And so this becomes a system of systems challenge, not just a systems challenge or a vehicle design challenge. And then on the right-hand side is the indication of just how important alternative propulsion cycles and advanced engine cycles are, and the opportunity around multi-fuel and dual fuel, and leveraging the benefits of cryo while also essentially benefiting from the potential life cycle production reductions to emissions at the same time. And so there's quite a bit of work going into this as well with partners across academia and industry. In order to protect the future of aviation, to be sure that we in this country and globally can continue flying, continue meeting the demand for air travel and operating in this global aviation system, is going to require solving quite a few challenges. I've listed some of them here. This isn't exhaustive by any stretch, but advanced propulsion cycles, and I'm talking cryogenics, but I'm also talking advanced fuel cells, water injection, open fan, open rotor, a lot of options out there to improve propulsion efficiency. Thinner, lighter, stronger, advanced wings, and perhaps those are trussed, perhaps they're not. Digital engineering, like I said. Propulsion airframe integration, PAI, is going to be an increasingly challenging problem to address as we move to new configurations. Contrails, if you've heard of contrails, if you've seen contrails in the sky, these are those clouds that you sometimes see forming behind aircraft as they fly by. Contrail mitigation is going to be really key, and that's a really difficult system of systems problem because it's a function of the vehicle technology, what's coming out the tailpipe, local weather, and other things. But there's a big opportunity there. Airports that are perhaps underutilized right now in the United States could provide nodes for energy production, for regional air mobility, perhaps a rethink of the hub and spoke model. Like I mentioned earlier, system of systems analysis and the need to consider more and more The dependencies outside the vehicle system itself are going to be key. And materials and structures. Materials and structures have such a huge benefit, foundational benefit across aerospace, and especially now with especially advances in AI and the ability to engineer materials with properties that you actually need is a huge challenge and opportunity. So in order to be successful, we need to push beyond what I would call long-held assumptions on what it means to design an aircraft, to operate an aircraft, to fuel an aircraft. It's going to require revolutionary engineering methods, as well as pretty strong industry-academic partnership. And a fourth bullet I would add is it's going to require a really strong next generation of engineers. These challenges are immense. And as much as we can prepare for the future with you, students and beyond, the better. So I really do believe that aviation sustainability is probably going to be the challenge of the century for commercial aviation. But that's not all we do. So at NASA Aeronautics, what I've shared here is the work that my program has done predominantly in one of 4 transformation areas that we're trying to enable. And that would be the transform airframes and propulsion box in the top left there. But we're also trying to pioneer high-speed flight. If anybody's seen the X-59, the Quest, the low-boom flight demonstrator, we had a first flight a couple months ago, really exciting. Supersonic aircraft, doing a lot with hypersonic aircraft if you're interested in going even faster than the speed of sound. Revolutionizing aerospace engineering methods and understanding how to bring to bear AI, machine learning, data fusion to accelerate the design cycle is going to be really important. And then also the system itself, the aerospace system operations, and how we increasingly automate and make more efficient airspace and safety. So there's a lot there, and I want to end by acknowledging both NASA Aeronautics, Research Mission Directorate, where my program sits, one of 4 programs, for their support, and especially to the National Academy of Engineering for the opportunity to be here today and share this work with you. I really, really appreciate it. And if you want to follow us, there's Thank you. There's lots of opportunities to connect with us. Here are a few, and there are many others if you go to nasa.gov. I'm happy to take any questions.
Yeah, so we have time for several minutes for questions. Again, we have roving microphones, I believe. Are there roving microphones? There should be, because there are people watching online. All right, thank you. Thanks, Elena. Okay, are there questions first on that side? All right, thank you. And then keep your hands raised so we can bring the second microphone to you. Okay. All right, please go ahead on the right. Yes, please.
Thank you.
Hi, my name is Anthony from Semele Academy. You kind of mentioned this a little bit more like in the midsection of your presentation about like the changes surrounding the infrastructure of these aircraft. But my question to you is like, what changes do you foresee in terms of like airports and runways, as well as maybe the personnel that would be in charge of maintaining these newer, more advanced or alternative aircrafts?
Thanks for the question, Anthony. So we have to think a lot about this because we don't want to make technology decisions that we know might be dead on arrival if we can't solve the infrastructural challenges. And a couple of things that I mentioned in my talk that we're exploring right now, I think really beg this question. So one example would be if we go to cryogenics, cryogenic hydrogen, or let's say cryogenic methane, natural gas. The operations, the standards on airport, the pipelines themselves that carry fuel to airports, the processing capabilities on airports, there is so much that would need to change. And you might think to yourself, wow, that sounds insurmountable, way too costly. How in the world are we going to do this? I would argue that aviation will probably benefit from other industries along the way. And so aviation as a transportation sector, there's a really interesting intermingling when you start looking at how aviation fuel is produced, where the refineries are, where petroleum products go, and in what form and how. Same with airports, and you look at the requirements that drive on airport operations and standards and designs. I think there's going to be a continued tension between the near-term realities and the far-term opportunities. One example from a discussion I had not too long ago with somebody who spends a lot of their time at airports working with an airport authority in this country, the question of electrification came up. And when I say electrification, I mean hybrid electrification or at least more advanced electrified aircraft propulsion. Because electric can be very efficient even if batteries are very heavy. So I don't necessarily mean batteries, but electric came up. And we were having a discussion and said, what are your thoughts on what it would take to electrify airplanes? Let's say we want to carry a small battery to do something we call mild hybridization, where we use the stored electrical energy to improve the operability limits of the turbo machinery. So it's not like you're just getting rid of the turbofan or anything like that. And the response actually took me back a little bit. The individual said, how can I think about that when I don't know how I'm going to reinforce my parking deck for the EVs that are in the rental car fleets now? I said, oh my gosh, okay. I hadn't considered that at all. But that's a very near-term problem that airports will have to solve as, let's say, rental car fleets continue to go electric. Longer term, there's going to have to be cross-agency partnership. We'll have to work with the FAA, DOE, and others to ensure that the system and system level enhancements are being made alongside the vehicle technology. It's also a chicken and an egg sort of dilemma. So there's a natural tension there. I'll just maybe leave it at that and say that we're thinking about it. It'll require national partnership to solve it. It's not insurmountable, but there's going to be a tension between the near-term realities of operations and the far-term opportunity around really disruptive technologies and how we actually process and, for alternative fuels, for example, actually produce, transport to the airport, refuel our airplanes, keep them safe, and the list goes on. Thank you for the question. Yeah.
Hi, my name is Ramses Demas. I'm an 11th grader at Cabrillo High School in CED pathway. And my question for you is, what is the most important life lesson you have learned to shape you into the man you are now?
Wow, oh my gosh. Yeah, y'all aren't holding back. Most important life lesson I've learned. On the spot, top of my head, is don't assume you can't do it. Simple, okay? Don't assume that you can't do it or that it's impossible or for any reason you shouldn't try, okay? And yeah, I can think of a million examples that I probably won't relay in front of an entire audience right now, but a million examples where I had doubted myself. And if I go back to my comment earlier about mentorship and why I really want to stress that so much, is if you can imagine everything you understand, the mental model you have about the world, about technology, about science, whatever we're talking about, I mean, it's really driven by your life experiences. We all have different life experiences. And it's so valuable to have a mentor who has had different life experiences. And he or she can look at your situation and say, well, you're not even considering option D, right? So I think in short, I would say, don't assume you can't do it. I'm sure you can. Is it going to require a lot of work, just like Eric was talking about earlier on the stage? Absolutely. But it's possible. I'll leave it at that. Sure.
Good afternoon. My name is Colin Yang from Cabrillo High School CED's program. My question for you is, as an engineer, of course, you come up with brilliant ideas, especially in aeronautics, but how do you find the middle line between dreams and reality for you to make that idea a reality?
Let's see. tongue-in-cheek response, my management will tell me, or my budget won't support it. So this is especially tough. My background in aerospace has largely been in the conceptual design and aircraft configuration space. And if you think about aircraft development, that's like the first step on the train to actually producing an aircraft. And it's not the first, there's systems requirement development, all this other stuff that comes first. But it's the first stop. It also means it's probably the most uncertain point in the process. And I don't have it in front of me, but I'm picturing a graphic from a textbook that I often shared in my classes when I would teach cost analysis. One of the things that you learn in aircraft program development is conceptual design is really important because most of your committed cost is happening that early in a program. And so that's why my tongue-in-cheek response is management and budget. But really, it comes down to the ability to model. So either from a physics point of view or from like a systems point of view, what you're after. In some cases, you don't have the physics at hand, and AI is an interesting new tool that we're all learning how to use right now, but we also are surrounded by subject matter experts. So one thing that we often do in the systems analysis world is something just called subject matter expert elicitation. So we just ask really smart people that know a whole lot about very specific disciplinary items, and then we roll that into our models in ways that we can quantify. I mentioned earlier uncertainty and uncertainty quantification. This is a growing field within aerospace and actually many engineering disciplines because we know that the answer is wrong, but we need to know how wrong it is. And so we all agree on that, and we all understand there's uncertainty, and now I think there's a concerted effort to quantify that in our programs. At the end of the day, it comes down to a judgment call. And it's a combination of the physics, the engineering, and the stakeholders. And stakeholders can have wildly different expectations and requirements. I shared the airport example earlier where we were on completely different planes of the universe, it felt like, at that point in the conversation. So it's a balance, and it's a decision. And if you're interested in decision analysis, there's a whole field of decision analysis and how you can use that as part of the engineering process. I don't have a great succinct answer to that one. It's hard, but you have to realize that the answer is wrong, quantify how wrong it is, do an analysis of alternatives, I would say, an AOA, understand what your options are, and then through budget, cost, schedule, et cetera, figure out what you can advocate for and think you can achieve in the time frame that you have to achieve it. I talked earlier about pretty long time scales, 20 years. Interestingly, the NASA budget is really a 2-year budget. So we don't know how much money we're going to have every 2 years. And so it's really important for us to understand from an alternatives point of view, from a trade sort of point of view, what our option space is, and then do as much as we can with what we're provided. So it's good to have a vision, and then it's good to have near-term wins and a strategy that gets you there. Thanks for your question. Okay.
All right. All right. Thanks so much, Jesse, for enlightening us to the challenges and opportunities for transforming aviation. And thank you to the students for, again, really good questions. We wish you all the best in continued success.